Hi, and welcome to Chapter 12. Last chapter we covered subnetting, so this chapter we're going to continue on with some different transmission modalities, a couple new protocols, and a couple of other things to help get our data from point A to point B. Let's get started. Glancing at our roadmap for the class, you can see that we're finishing up our addressing transmission section. After this, we'll go into some alternate access and administration, but we're getting through it. So to start with, let's talk about sending voice or audio across the internet. Video and voice actually represents the largest amount of data transmitted. Not so much because there are that many more pieces of information, but because the information is so large. If you think about it, every video through YouTube or any of the streaming services, Netflix, has to send an obnoxious amount of information across, whereas sending a single file or an HTML file is really quite small in comparison. So first off, let's start talking about voice and audio signals. If I'm going to send you a voice signal or an audio signal, it starts as an analog. Analog being a wave. That's how we speak. We speak in waves. And we need to convert those into digital. We covered part of this in Chapter 1 when we first started introducing this. Now we can bring it back. When we look at a single wave pattern, so a voice analog pattern, it looks like a wave. It goes up and down and has different amplitudes. The number of times we take a sample in a given period is called our sampling rate. How many samples are we going to take in this period of time? And the period of time can be long or short depending on whatever we choose to do. Obviously, the more sampling that you do, the better, because as you can see from the low sampling rate and high sampling rate in the image, if we only selected say 10 as opposed to 20 sampling positions, we wouldn't get all of the ups and downs. So the more sampling you do, the sampling rate being higher, the number of times the sample is taken in that period, the better your quality is going to be. Our bit rate is how many bits do we want to use to represent that amplitude. So if we look down, straight down at the bottom where we have our voltage levels and our binary codes, you can see that in one case we have 4 bits, and one case we have 8 bits. The 4-bit bit rate can only do a single volt per bit code. So starting with 0, we'd have 0 volts, 1 would be 1 volt, 2 would be 2 volts, and we can only do them on increments of a single volt. But if we store them in 8 bits, we can actually have 256 levels for those 16 levels of voltages. So if we have voltage of 0.05 volts, we can represent that as 1 in binary code. Being able to have more bits is going to allow you to represent each voltage better. If you get all the way up to 16 bits, you're looking at 65,000 levels, which means each level, each amplitude is going to be able to be represented much better. So being able to have the bit rate is how many bits does it take to represent that amplitude. The next piece of information is what we call our sampling frequency. This is a rate that determines how the amplitude is measured per second. So the rate that we check it per second, not in a given period like our sampling rate, but our sampling frequency is measured in hertz. So a frequency is measured in hertz. It's per second as opposed to a given period of time, which would be our sampling rate. So when we think of that, how much is a normal sampling frequency? Well, just to give you an idea, the human voice is usually sampled at 11 kilohertz, which is 11,000 times per second, which means every second there's 11,000 times. If you did really high quality sound, you're getting up to 44 kilohertz or 44,000 times per second that you are checking those signals. This is going to give you a really good idea of how the sound is going to come across, and the difference between normal human voice and those really high quality CD, DVDs type things. You can see in the bottom right-hand side one of the options that we had for storing sound data coming into a microphone. You could choose how many channels did you want, how many bits did you want to store it at, and then how many hertz or kilohertz did you want to store? And you can see how they have CD quality, DVD, studio quality as options. So you can get up to some pretty significant amount of hertz. However, there is a drawback to going to higher hertz. When we're talking about our audio and visual terms, so these are just words that I need you to understand. We're going to use them frequently when we talk about both audio and video, so I need you to make sure you understand them. First is jitter. Jitter is simply that hesitation in your delivery sequence of your audio or video. This is caused by latency or missing packets that might get lost somewhere. So if you're watching a movie or a video and you see small little hesitations, those are called jitter. Latency, which is a cause of jitter, is simply that the delay of data as it reaches its destination. We're sending data out from the source, it's going through the internet to get to you, and then it's ending up over on your destination. We can mitigate latency by buffering, which means when you download a video from Netflix, it buffers, say, the first 20 or 30 seconds so that it doesn't have to have that delay obvious to you. Small breaks can actually go unnoticed. If you have less than 150 milliseconds of latency, you probably won't notice it. Your eye is not going to catch it. If you're at about medium, so if you're at about 250 milliseconds, you may notice them, but you can tolerate it. You'll go with it. It's not going to make you shut it off and turn it back on again. If you have large breaks up to 500 milliseconds, a half of a second, those are unacceptable. People will notice that and they will be annoyed. So when we think about latency, small amounts of latency are okay. We can go unnoticed, especially if we have buffering. When you start getting into large, half a second, those are not going to be okay. Another problem that we can have in sending data across is what we call an acoustical echo. This happens, you'll find, if your microphone and your speaker are too close to each other and it causes feedback. It can also be caused by voice over IP latency. And usually it can be resolved by fixing your settings, changing your volume levels, or moving your devices around on your desk. If you have a segregated microphone and speakers and you're having problems with those causing some echo, you can separate them, move them to other sides of your desk, and that might help to solve it. There's actually an entire field called digital signal processing that purposely handles the concept of being able to process your digital signal through your equipment, making sure your equipment, your microphones, your speakers, so on and so forth, are all going to work well, processing your digital signals and making those sound well. When we talk about video, so back in the olden days, video is technically just flashing of images faster than you can detect it. Take a deck of cards and you run them through with your thumb. You can make it look like the guy is moving across the cards. It's just images, flat images, being sent faster than you can recognize that they're being sent. Generally, movies can run at 24 frames per second. 24 frames per second is about the minimum that you can run a movie and have the user not detect it. Any lower than that, they're going to see it. They're going to feel a flash. But if you go at 24 frames per second, you should be fine. When you think about what else is considered other than the frame rate itself, 24 frames per second, we can think about the resolution. So a little bit of math for a second. If we did full color VGA, which is 640 by 480, which is not very high quality, it's okay quality, but it's not great. And we did it in full color. Full color uses 32 bits. We do 640 by 480 to get the area, so each pixel. Each pixel needs 32 bits to hold its color. And there are 24 frames per second, which is roughly 24 megabytes of data per second. If you have a 3-minute cat video on YouTube, it is 4.3 gigabytes of data. That's a lot. So we don't usually send it like that. We compress it. So we use compression. Codecs, compression, decompression, is a piece of software that is going to compress or decompress your video. It'll compress it from the source, send it to you. Once it gets to the destination, it decompresses it, and we watch the video. MPEGs are the motion picture expert group, and they have created 3 versions of their MPEG software, or their MPEG protocol. The first, MPEG 3, is a low resolution. It's really only about 320 by 240. And when it gets created, it's really going at about 1.5 megabits per second. So it's not a whole lot of data, but it's also very low quality. This is fine if quality isn't the problem you're looking for. So this works really well if you have a low resolution situation. MPEG-2 has been the standard for a while until we got to MPEG-4. It's higher resolution, so it's 720 by 480, and it can run at about 6 megabits per second, or megabytes per second. So faster, sends more data across, which is great, and a better resolution. Again, 720 by 480 is not very high when you're looking at HD TVs that are going up to, 4,000. You're really, 480. You're looking at a lot more data there. MPEG-3, it's not on the slide, but MPEG-3 was supposed to handle HD TV, so high definition TV, but it just didn't work, and they kind of realized that MPEG-2 was doing okay, so they just canceled it. So MPEG-3 actually got canceled because it wasn't necessary, it wasn't doing the job. MPEG-4 is now the new standard for multimedia. It can go at a rate of 1 gigabit per second, which is so much better than the MPEG-2. And it's kind of what we use a lot for internet, streaming, data, so on and so forth. So the different compressions are used in different situations, and there are still reasons to use MPEG-1 or 2. But in general, your internet's going to be using your MPEG-4. There's a couple of other ways to transmit data across the internet. X25, X.25, actually uses an analog signal to transmit data over long distances. It kind of feels counterintuitive in our generation, but remember back in the early years, analog was how things were being transmitted anyway. Voice signals were always done in analog. So being able to use an analog signal to transmit data, which feels a little backwards now, was actually the way things used to go. X25 actually used packet switching as opposed to circuit switching, and it was limited to about 56 kilobits per second. Pretty slow, but again, at the time, being able to send data using analog was pretty awesome. Next, we came up with the frame relay, and frame relay was designed to replace X25. Frame relay was designed to use T1 lines over long distances, and it sped up to data rates of 1.544 megabits per second, so a lot faster. When you use either the frame relay or the X25, you can create what is called a permanent virtual circuit. It behaves like a hardwired connection, kind of like a T1 line, but it isn't committed to a single path. So it creates a connection between two locations, a permanent circuit, but it's virtualized, and it allows it to use multiple destinations or multiple paths, so it isn't a straight path like a regular T1 line. Another thing to keep in mind with transmission is our committed information rate. This is a guaranteed bandwidth, and some people get a little confused thinking it's like guaranteed information rate. It's CIR, committed. The ISP has committed to you that they will keep this minimum bandwidth for your subscriber. If you're using a T1 line, they set it at 1.544 megabits. If you're on a T3 line, it's at 45 megabits. This is your guaranteed bandwidth from your ISP to you, and you can talk to them about asking for the committed information rate to make sure you know what is the minimum guaranteed bandwidth you are giving me. At this point, we're going to move on to ATM, asynchronous transfer mode. We've already introduced this to you a couple of chapters way back at the beginning, but we're going to bring it up now because ATM is used for audio, video, and multimedia, moving pictures and sound across the internet. So let's focus a little bit more on ATM for a couple of slides and see if we can understand how it's done. First off, ATM is generally the backbone of most cable companies. They're going to use ATM specifically because it is so well defined for audio and video. We can use converters using individual chips that will convert from analog to digital and digital back to analog. And it's a chip that can go on your motherboard. So when we think about ADC, it's an analog to digital converter or a digital to analog converter, and it's a chip that sits on your motherboard. It allows you to use the chip to be able to convert from one to the other. ATM is connection oriented. It is not connectionless. It makes a connection. So there is a connection that goes between 2 points when you're using ATM. When you're using ATM, you can use either a constant bit rate or a variable bit rate, CBR and VBR. If you use a variable bit rate, you are going to be using multiplexing. So a CBR is a constant stream of data that we use for video conferencing using a virtual circuit to be able to keep a set stream of data coming across. Variable means that it changes. It could be faster, could be slower based on whatever your data is. We're going to talk a little bit more about different types of VBR in the next slide. But the visual here is you have two different pieces of information going from the source to the destination. One is a text document and one is some audio or video data. Both of them are going to go from the source into a multiplexer, where the multiplexer is going to be able to combine them together. Remember, a multiplexer is going to take two different streams, convert them into one stream, and be able to send the packets traveling through your line. ATM is connection, so it's going to have a dedicated common line. So these are both going to be going through. And then when they get to the destination, the demultiplexer is going to split them back out into the text document and the audio visual. So we can get the audio video in one location and the text in another if you need these to come across separately. So that's the basics of how data is going to go through a multiplexer, be converted, run through packets, and come back out when you use ATM, asynchronous transfer mode. A couple of things with ATM. ATM can use its own switches. So they are ATM switches. They are designed to use ATM and to build that virtual circuit between your connections. So ATM is a style that uses its own hardware, its own switches. The different transfer classifications, and this kind of goes in cost from highest to lowest. We talked about constant bit rate. This is constant. It stays at the same bit rate and it's always transferred at that rate, which is probably the most expensive because you're constantly leaving it up whether or not you're using it. Your variable bit rate real time, or RT, is designed to support real-time data rates. So things that need to go real-time, those will be there. Those will be a little bit more expensive than your variable bit rate non-real-time, which also allows a variable rate depending on what data. If you're sending text files, we're going to go slower. If we're sending video calls with voice, we're going to go faster. So our variable bit rate is going to adjust as necessary in these situations. The variable bit rate non-real time is generally used for streaming of videos. You still want it to be quick, and it's important that the timing stays there, but it isn't a real-time thing. You can do buffering. The next is ABR, which is available bit rate. This literally says whatever is available, go ahead and use that, and I don't care. So it's fine. We can use whatever available bit rate that exists. This is usually used for file transfers because it just uses whatever the current traffic is that's on the network. Yeah, let's go with that bit rate and we'll go there. And the last one is an unspecified bit rate. This could be anywhere across the block. There is no guarantee for the speed. And this is usually used for your TCP IP frames. We're going to use an unspecified bit rate for those. When we make our ATM cell, it's actually kind of similar to a UDP cell. It's very, very simple. We have a 53 byte cell frame that you're going to be working with. We call them cells in ATM. And it's going to have this 48 bytes of payload and 5 bytes for your header. The header is going to include some flow control, some path identifier, some channels, what type of payload is it, cell loss priority, and header error control sections. So these are going to fill up that 5 byte header. Remember, each byte is 8 bits, so you're looking at 40 bits that we can put in here. So 40 bits or 5 bytes for the header, and then 48 bytes for your payload. And so it makes this 53 byte cell design very efficient, very quick to just run across nicely. Okay, we've talked about ATM. Now we're going to introduce voice over IP. So voice over IP, VoIP, where the O is lowercase, is also sometimes called internet telephony because we kind of use voice over IP as a way to call on the telephone using the internet. So it's another word for it. It's very similar in its design of ATM, but it relies on the TCP/IP protocols, the equipment that uses TCP/IP, the technology, so on and so forth. When you use voice over IP, you can transmit in either TCP or UDP. This is one of those feels backwards situations. TCP is connection-based. Well, if we're doing voice over IP, don't we want connection-based? Funny thing is, UDP is actually used more often in voice over IP. The reason why is because TCP/IP requires you to respond and say whether or not you got it. If you didn't get it, you need to send it again, and that can cause latency. It can cause things to take longer. It also increases the amount of bandwidth exponentially. Every single packet with TCP would have to be checked and verified, and it could take up too much time. So the funny thing is, we use TCP when we're doing voice over IP to set up our connection, to do our registration, take care of our firewall, make sure that we use that all in our setup and our session initiation. However, UDP is usually what the packets are made in, that we send the voice actually over the internet. Because for efficiency reasons, it doesn't resend lost packets. We're just going to accept it that this packet didn't go through. If your bandwidth is really bad, that can cause issues, which is why if you're running a Skype call and everybody's got their video on and everybody's sending those packets, it can be slower and jittery. If everybody turns off their video and just does the audio, it takes up less space and works a little bit better. So in general, when we think of TCP versus UDP, TCP is generally used for accuracy. You need to verify. Whereas UDP is done because it's faster. In the situation of voice over IP, speed is more important than accuracy. So when we're talking about voice over IP, we really need a high bandwidth. Generally, you're going to want fiber or at least a gigabit Ethernet. There's a lot of options for voice over IP. You can simply communicate between two PCs using the TCP IP. That's your WebEx or your Zoom or your Teams. You can mix TCP IP telephone with existing telephone. You can call a landline, and you can communicate from your computer, your PC, to a cell phone using both your LAN, your PSTN, which is your public switch telephone network, or some people call it the POTS, the plain old telephone system. This is your basic phone lines. And then using wireless technology to talk to a cell phone. So you can have multiple technologies going for voice over IP. In voice over IP, we sometimes have a piece of software that is going to be called a bandwidth shaper. It's also a traffic shaper. And it's designed to prioritize your packets to make sure that the ones that have to get there first, and they're prioritized to ensure your quality of service. We'll talk about quality of service in just a second. So, since we talked about voice over IP, we're going to move into the telephone system. So telephone gateways are equipments that connect your packet style communication that we've been doing with the internet to a telephone system. How do we get things onto my PSTN, my regular telephone system? We can use the H323 gateway, which is an older standard for audio, video, and data using IP. Using packet type. This was designed by the International Telecommunication Union, the ITU, and it includes a suite of protocols similar to TCP/IP that has a suite of protocols. So the H323 is going to be used to connect to your old telephone system if necessary. So if we need to connect to the telephone systems, this is what we're going to use. There's a standard protocol called QoS, or Quality of Service, which is purposely designed to minimize latency. The whole purpose of the protocol is to minimize your latency. So we're going to reference QoS a couple of times. Along with QoS, we have CoS, which is your cost of service, as opposed to your quality of service. Sometimes the cost matters, sometimes it doesn't. A couple of other protocols would be your ATM over IP and your frame relay over IP, which is similar to your voice over IP in the sense that they're another protocol that's going to explain how to use ATM over IP and frame relay over IP to get in that IP protocol. So two of the protocols that we use in voice over IP and some of these other ones are going to be your session initiation and your real-time transport. So your session initiation, SIP, session initiation, this all has to do with initiating and terminating the session. We need to have a communication session going on. And how I said you usually use UDP with voice over IP, this is where TCP comes in. You might use TCP to set up your initiation protocol. And the port for TCP is going to be your 5061 as opposed to 5060. Generally, SIP doesn't charge you anything if you're connecting to a soft phone. A soft phone is a virtual telephone. So a virtual phone that is on your computer that is not a physical telephone It's called a soft phone, and generally there are no charges with that. But if you're going to go through the regular phone system and touch a regular physical telephone, you might have charges applied. Sometimes with Skype and some of these programs, you can do virtual calls over the internet as long as you're calling over internet and you're going to a virtual phone, as opposed to calling to an actual phone number. So SIP is going to set up the initiation and terminating of the session. It's keeping track of the session variables, session things you need to keep track of. Your real-time transport protocol, RTP, real-time being one word, real-time transport protocol, is worried about delivering your packet as fast as possible. It's all about speed. So RTP will use UDP, which doesn't have any guarantee. Voice and video conferencing, gaming, these are all going to be using UDP packets, just sending them as fast as possible so that you can get them as fast in real time as you can. The control protocol that's used with RTP is the RTCP, Real-Time Transport Control Protocol. There's also a couple of other protocols. The SIP obviously is used to initiate the session, and then a couple of other H protocols. There's also a secure RTP and a compressed RTP. So SRTP and CRTP. These are secure and compressed versions of real-time transport protocol. If you're using your voice over IP and you're having trouble with it, there's a couple of things that you can look for. First off, use a protocol analyzer just to verify that your packets are getting exchanged correctly. You can check your options on your router, your switch, or your gateway to make sure that you either are supporting or at least enhancing your voice over IP. You can tell your router, hey, I'm doing voice over IP over my router. Can you please make sure it works well? Sometimes your firewall may be blocking those packets, so you need to also check your firewall to make sure that it's open for voice over IP packets across those ports. Sometimes your audio device configuration is screwed up. Sometimes there's some problems with your microphone or your speakers. Make sure that those obviously work. I would say that's probably the biggest problem with people who are on some sort of voice over IP, some sort of communication with Skype or Teams or whatever. Their microphone isn't hooked up correctly. Fix your microphone, make sure it's configured. And the last one is what we call impedance mismatch. By the way, the word is impedance with an A-N-C-E, impedance. Just so that if you get this on the test, you don't spell it wrong. This is where you want to make sure that you're not using a 2-wire phone cable with your 4-wire phone circuit. This can cause echo and it can cause problems. So if you, back in the old days, there used to be a 2-wire that came in a 2-wire adapter for your phone, turned into a 4-wire, which we use more for data. Make sure that you aren't having a mismatch of your actual cabling. Okay, so the end of chapter 12. First, obviously, I recommend the review questions. Your study guide is going to be 1 through 18. Go ahead and fill all of those out. For the lab for chapter 12, there's really only one of them, and I'm not actually requiring it. The lab is going to be using a piece of software called TeamViewer that is designed to communicate between 2 computers, essentially setting up remote desktop between 2 computers and being able to do that. You are welcome to do this lab so that you understand the software, but I don't think it's going to be necessary for the purposes either of the Network Plus test or for you to learn enough information. It's just a piece of software that you can use. So you're welcome to do it, but you don't have to turn it in if you do. Again, the study mate's always there, and don't forget to take the quiz. I hope you learned a lot in this chapter 12 on different types of transmission. ATM is a really important thing for the Network Plus test, and being able to understand ATM and voice over IP, how data gets moved from point A to point B, is really, really important when it comes to audio and visual. Please come back next time for chapter 13. Have a great week.